So for me, it's an honor to moderate this session together with Brenda. And we are happy to present our keynote lecture by Mauro Carolli from SINTEF. I think it's not needed to talk about SINTEF and tell you what they are, who they are, what they are doing. That's self-explaining. But I think the keynote is very important because Mauro was working on hydropower development in the Balkan region. And I think that's a very important contribution to this conference.
Hey, good morning, everybody. Thank you for the introduction. And yeah, can I have the pointer here? On the behalf of all my co-author, this morning I will talk about the effects of barriers in general, but especially of planned hydropower dams on river connectivity in the Balkan region. Why connectivity and fragmentation? Rivers are, we know, are the ecosystem with high biodiversity. The natural river processes, they depend on the flow of water and sediments. This is the famous sketch from Condolf that shows how the river transports sediments downstream and shapes the landscape in which we live. But they also provide a large range of ecosystem services to the human activities. Here I put just some of them: navigation, water supply, recreational activities, hydropower. Debatable if it's an ecosystem services. Many do not agree, but let's leave it there. Habitat for species, climate change mitigation, temperature mitigation, etc. Many of these activities for which we profit requires the construction of barriers. So what are barriers? Barriers are everything that blocks in some way the river connectivity. This is the other famous figure from Condorf. It's an adaptation from the old one, where they show that building different barriers changes the river processes and decrease river connectivity. When we talk about barriers, it might be longitudinal barriers like the dams. You see it up there. But also barriers that break the lateral connectivity. The levees, for example, that disconnect the river from the floodplain, which in many cases is exactly what we want. Or, for example, the concrete channels that disconnect the river from its groundwater, so it interrupts the vertical connectivity. So the question was, how many are these barriers? Do we know it? And where are they? Because it matters if it's up in the catchment, lower in the catchment, which type of barrier? There's a difference between a large dam and a small weir. So the Amber project was an Horizon 2020 project. It's finished now since a couple of years and conducted the assessment of river connectivity at the European scale. We collected 120 databases from many different countries and consolidated them in a unique database. And the barriers are grouped in 7 different types. So the barriers were consolidated, 7 different types. Here I have just some pictures. It goes from very low head barriers, like this one is always underwater. This is a bed seal ramp. This is a river in Norway, actually. But also large barriers for hydropower production, like this one is under construction. And a type of barrier that is usually a bit doesn't go a bit under the radar is fords. They are really common in some areas, and they completely block the river, like in this case, this is Albania. So in the consolidated database, we had 630,000 barriers. And the next question was, is this number correct? Are they really 630,000? So we developed a correction factor based on 2 different factors. We ground-truthed the databases, so literally walking around the river in selected stretches and mapping the barriers that were there and comparing with the database. Are they in the database? And then we using anthropic and environmental predictors and combining a machine learning method with model the barrier density. The result was that the barriers are probably very likely twice than the reported, so which is more than 1 million barriers. This is translated into a 0.74 barriers per kilometer, which is almost twice, obviously, the density we had in the database. If you want further information, the Amber site is still there. You can download the data from on the Amber Atlas from this site, and that's basically the paper that summarizes all the work has been done in the project. Then why the Balkans? The Balkan River Network is extended as much as France, as we saw, I discovered yesterday, but it's very diverse. So we go from headwaters to what is probably the European largest river. It's a biodiversity hotspot. The Balkans are rich of endemism, and as far as I know, many species are still not described. But probably one of the most important points is they are considered the home of the last Europe free-flowing rivers. Is this true? It depends what we intend for free-flowing. We saw yesterday from Wouter there's still an ongoing definition. We found more than 3,000 barriers in the Balkans, so they are not completely free-flowing, of any type. This is not only hydropower. I will talk about only hydropower later. This is every type of barrier, weir, dams, forts, etc. But when we surveyed the rivers in all this area, we discovered that they are vastly underreported, the barriers. We go from a 40% error in Slovenia, the minimum, which means that 6 out of 10 barriers were reported, to a 98% in Albania, which means that only 2 out of 100 barriers are in the databases. So again, the barrier density goes from 0.01 to 0.33. The total number is more than 20 times the barriers. But are they free-flowing? No, but they are more free-flowing than the rest of rivers in Europe, because the average number of barriers in the Balkan is still much lower than the European average. Another reason to pick the Balkans for a more detailed study is that it has a large unexploited hydropower potential with almost 3,000 new projects in the area. These data come from a WWF database and has been integrated with data at the local, at the regional scale, national scale. So you see here how the number of barriers explode. And interestingly, out of 3,000 barriers, 91% almost is small barriers, which means they are built with the aim of producing of an installed capacity of less than 10 megawatts. So small hydropower plants. So we guess, what's the impact of, what will be the impact on connectivity of these new built 3,000 barriers? So first of all, how do we quantify connectivity and fragmentation? We choose 4 matrices. There are many matrices. These are quite common, I would say. So the barrier free length is the length between 2 barriers, and is a property of the reach. So in one catchment, we have many of these segments. There's the length max, which is the length of the longest free barrier segment in the catchment. So this is a property of the catchment. But this metric needs to be standardized to be compared among catchments, which is the BFL max. It's just the longest segment standardized by the length of the catchment. And then there's the dendritic conductivity index, which is the probability of that a fish can move between 2 points in the network. And it gives a measure of, again, of fragmentation. We use only the version for photodromous species in this case, not for the anadromous and catadromous. It's a bit of a different, then the index becomes a bit different. But we need to assess if there's a real fragmentation to quantify. We need to compare it with something. So first, we built a reference scenario, which is the current state. So how much is fragmented now? If we don't build anything, this is what we have. And then we built 3 future scenarios. They were more, but these one are the more interesting. So what happens if we build all the new barriers? What happens if we build only the barriers for large hydropower production, so the ones with installed capacity more than 10 megawatts? And what happens if we build only the ones for small hydropower production, so the small plants? Some results. This is the first metric, and okay, can't see it very well. So the first one is here, the existing one, and we use it as a reference. Here, the colors means red means is going worse. So the longest it is, the closest is to blue. As you can see in the existing scenario, there are still some blue catchment. When we build all the barriers, we have a decrease in all scenarios, especially in some areas. For example, the Adriatic catchments here, as you can see, they go quite, they lose connectivity. Compared to a large scenario, small dams have a larger effect. Again, if we look at this area here compared to this area here, the effect is quite clearly more evident for small dams. So we can see it also from the data. The existing average is 78 kilometers. If we build small dams, it almost divides by 2, 42, it goes to 42. Interestingly enough, this is close to the value of if we build all dams. I will go back on this. Very similar for the other metrics. So in this case, we have only one value for each catchment. It decreases in each scenario. Again, some catchments, the Adriatic ones, which are these ones, are more impacted. And in this case, the effect of small dams and large dams is a bit less evident because we lose already 200 kilometers in the average just building the large dams. Same for the connectivity index. The smaller difference between small and large dam scenario. Again, here the percentages are similar for the existing and the large, a bit lower for the small. So for the ones who like statistics, the scenarios were statistically different among them. And we can say that the river network is already fragmented, but if we build all the barriers, all future scenarios, whatever we build, the connectivity is decreased. Some areas are more impacted than others. So we saw the Adriatic catchments looks like are more, there are more projects planned there. And small dams have a larger and more widespread effect. It's quite trivial because they are 90% of the new barriers. So the next question was, what's the effect of these barriers, but in relation to installed capacity? So the small dams have a large effect. They are largely the majority, but how much do they produce? This is not a trade-off analysis. It's a comparison between two values. To read the graph, the 0 here, the origin, it's a negative axis. So the closest to the origin up there, the batteries for the y-axis. And here we have a loss in connectivity and installed capacity. The installed capacity doesn't start from 0 because this is the existing capacity. So the Balkans at the moment have 20,000 megawatts of installed capacity. And as you can see here, first we compare the different scenarios. If we build only the large dams, we have already the 67% of the total installed capacity. If we build only the small dams, which are the vast majority again, we have the biggest loss, almost 50% of the connectivity, versus only a 33% of the installed capacity. So it's already telling something that there's some barriers have a higher effect than a larger effect than other barriers when they have whereas they have a smaller contribution to the total production. We can also go to a final resolution, higher resolution. Here you can see there are some barriers that clearly have a higher effect than others. For example, this one causes a huge decrease in connectivity, but there's no contribution to the production. So let's go not one by one, but I will show you some examples. Of all these barriers, all the projects are planned in 61 catchments. But 70% of all these projects are only in 10 catchments, which are these ones. It's a big area, but it's not 70% of the total area. So they say they are concentrated in some catchments. It's just useful to just show you at least I just remove some background noise from one barrier, one basin, which is a bit difficult to read. Of this 70%, 148 are large plants. Interestingly enough, almost 1,300 are plants of less than 1 megawatt. So it's mini and micro hydropower plants. So then it's possible to summarize in a space like this. Again, we have the loss of connectivity versus the installed capacity, but is not cumulated, is barrier by barrier. The x-axis is logarithmic. That's why you have some negative values there. So here we divide it in 3 different areas. There's the yellow area, means low impact, low production, high production, high impact, high production here. Then there's the green area, which is where we want to arrive, this low impact, high production. And there's the completely avoid area, which is high impact, low production. This is the red one there. So our suggestion was, let's prioritize the projects in the green area. They have a huge production in some cases and a very limited impact on the connectivity and on the fragmentation. A bit more in detail, I will show you 4 catchments. 25%, 1/4 of the projects are in one catchment, which is the Morava catchment, is big. But out of these more than 500 projects, only 20 have high production. All the rest is between 10 and 1. As a short explanation, you see these lines here, which is 1 and 10, because it was not possible to retrieve all the data for all the projects. So some of them are just, we consider it as this is the maximum, is what they declared in the project, but they didn't declare we produce 1.5 megawatts. While especially for the large project, this is easier to retrieve. So we are confident that the large projects are correct. The 10 megawatts, they might be 9, or the 1 megawatt might be 0.9 or 1.5. Again, the Danube catchments, this is Bulgaria and Romania. Lot of small and mini and micro hydropower plants, only 3 with high production. The Sava catchment, again, is a bit better. It has 18 with high production, almost 20%. And then I picked the Viosa because it's a bit, let's say, flagship catchment, with 99 projects and 10 with high production. I think these are stopped because it's been declared national park. I don't know if it's official. But I want to point out this. There's one pumping project in the Danube that has the installed capacity twice than all the mini and micro in these 10 catchments. And it's 2,400 megawatts of installed capacity against, for the whole Balkan area, there's 1,700 megawatts for all the mini and micro. So it's a different scale. And the loss in connectivity that we have is negligible. So this power plant is along the main stream of the Danube, is already impacted. But these are the projects that you can say, okay, let's go for these projects, because they have a limited impact and a huge possibility for production. This is, remember, this is the installed capacity, it's not how much we can produce per year. This approach obviously has some limits. So here I talked only about longitudinal connectivity. We don't know anything about lateral and vertical connectivity. At the moment, there are no information. As we heard yesterday from Wouter, the EU Commission is working on giving us criteria how to define lateral and I think more lateral than vertical connectivity. We did not include barriers passability. So we don't know, because we don't know if these barriers are planning fish ladders and everything for sediment release. We don't know this. There's an underestimation for sure of the existing, of the effect of the existing barriers, because as I show you, we developed a correction factor, but we might guess how many they are in a catchment, the basin, but we don't know where they are. So if you need to analyze the network and fragment the network knowing where they are, we can't do it, not yet. this is an important point. Talked about the impact of small dams, but large dams, even if they have a high production and a minor effect on fragmentation in some cases, have a huge impact on flow regime, sediment regime, habitat fragmentation, etc. We know these things. So it's a weighting of the different impacts. And I think one thing that we often forget of, is that the local communities might oppose quite firmly the development of large hydropower projects. If you didn't see it, these movies about the Balkan, it's called Blue Art, the fight for Europe's Wild Rivers. It's online, it's free. It's interesting because some small communities really opposed the construction of the dams in their area. On the other hand, the effect of large dams is well studied. The effect of small dams is less investigated. We know many things, but especially the cumulative effect is not so well known. So maybe if we need to mitigate, we know better how to mitigate the impact of a dam as far as possible than the impact of hundreds or thousands of small dams and barriers. We know from the Alps, Austrian studies, cumulative effect of small dams might be more harmful than larger dams, so it's another thing to take into account. And I'd like to point out the effects are case-specific. We can't do, this is an analysis done on the river network, but if we decide to build, we need to go and see case by case what's happening. Some conclusions is like, as you see, most of the plant projects in the Balkan are small plants. They have a small contribution to the production, but they have a large impact on the fragmentation. With that simple trade-off analysis, we can help in identifying projects that we should prioritize, and obviously prefer projects with high production and low impact. If we build all the barriers, there's a conflict with the EU directives for the countries that comply with the EU directives in the area. Not all of them do it, not all of the EU, or they want to be member candidates. But if we build all the barriers, obviously the targets of the Water Framework Directive and also the EU taxonomy are not met. There's some case-specific effect. Another thing is just in many of the Balkan countries, the strategic assessment and the environmental impact assessment for hydropower projects is not mandatory. So they don't have to do it. It means that they don't know what will happen. There's no study done. And that's a thing they should really think to do. Just quickly, they move out from the Balkans, because I'm working in Norway, we are in Norway. The situation in the different countries is really different. If we see different European countries, completely different data availability, but also how the rivers were managed. This is Norway. The barriers are, the error is, it looks quite high, but it's much lower than many European countries. So it means that almost one barrier out of two is underreported. But on that, I have to say the large dams are very well reported. What is underreported is many times is the bed seals and the weirs. And just a preliminary analysis, I didn't do an analysis like the one for the Balkans here. We have the Glomma and the Drammen-Selva here, which are red and are very fragmented, is one of the area with the largest, I think, hydropower production, but also inhabited area. But there are some open questions about the dams and the barriers in Norway. So many dams here, for example, are built on existing lakes. And here, I don't know what's the contribute to fragmentation. So maybe an idea is to rerun this analysis, but splitting in subcatchments. In Norway, obviously, is as the salmon as the flagship species, most important species. So we need to consider the migratory routes. A barrier in the headwaters might have a lower impact than the one just close to the sea. This is not something that we didn't do in the Balkans and not even in Norway, but it's a question that is there. Another thing is that the geology of Norway is quite different, very different from the one from the Balkans. The Balkan rivers are very active and there's a huge sediment transport that we don't see at that scale in Norway. So was the influences of barriers on the morphology of Norwegian rivers. It's probably a different effect than in the Balkans, for sure. Last slide. For more information, we have these two papers that comes from the Amber project. One is the more than 1 million barriers is the summary at the European level. There you see some data country by country. The other one is about the Balkans, but what I wanted to show you is this. During the Amber project has been developed, this app has been developed, it's called the Barrier Tracker app. You can download it if you go often on rivers. Please do it. It's very easy to use. You take a picture of the barrier, give some very easy data. I think it's the barrier type, the height, and some other information. This goes to a database that helps us to validate the data that we already have. And I'm sorry, I didn't put the QR code, but if I put the QR code, it goes to my Play Store, and this might not be valid for all of you because it's country by country. So please search for Amber Barrier Tracker in your store, and I think you will find it. It should be available for every country. So I'm finished. Thank you.